Long ago, perhaps 10 to 20 billion years ago, when the universe as we know it did not exist. At that time, in fact, neither space nor time existed in any form we are familiar with today. This concept, admittedly hard to grasp, is at the heart of the new thinking about the structure, origin, and evolution of the universe. Recent insights by cosmologists, astrophysicists who study the universe's past and future, have shed new light on old questions. How did the universe begin, if it had a beginning? Why is the universe as it appears today? What is the ultimate fate of the cosmos? As physics approaches these questions, it is inevitably being pushed toward confronting riddles that once were the exclusive province of religion. The age-old question of whether the universe is a product of chance or design is reaching the forefront of scientific investigation. This may portend a great coming together of these ideas of science and religion, ideas that have often appeared to conflict. Virtually all astronomers now believe that the universe sprang forth in what is known as the Big Bang explosion, from a state of great compression and phenomenally high temperature in which forces such as gravity and electromagnetism were unified in a single, all-encompassing force. But for most of the century, scientists puzzled over this. Why, if its original state was chaotic, is the universe of galaxies as uniform as it appears? Why is the universe precariously perched between expanding infinitely and collapsing back on itself, between being conducive to life and being inhospitable to it? The recent, surprising progress towards answers to these questions has been made possible by the increase in physicists' understanding of the connection between the biggest and smallest things in the universe. Through the work of astrophysicists and particle physicists, it is becoming possible to meld together the realm of stars and galaxies and the world of subatomic particles and waves, and to derive theories about their common beginnings. The most remarkable insights of recent years came from a young theoretical physicist at the Stanford Linear Acceleration Center, Alan Guth, who in 1979 developed an inflationary theory that explained the first fractional second of the universe, the coming into being of matter, and many puzzling features of the present cosmos. In effect, the inflation envisioned by Guth set the Big Bang in motion. He explained how the matter and energy of the visible universe and beyond originated from literally nothing. Thus, his theory holds the promise of showing that the present form of the universe is the inevitable consequence of physical laws that predated the cosmos. In his theory, arbitrariness and chance are removed from the creation. It is perhaps not too presumptuous to suggest that the concept of cosmic inflation unifies God and physics. The enormous scale of the universe was not recognized until the 1920s. William Herschel, the 19th century British astronomer and discoverer of the planet Uranus, had speculated that the fuzzy patches of light in the sky, seen through telescopes, were island universes, much like the Milky Way galaxy which the Sun appeared to inhabit. This was not confirmed until American astronomer Edwin Hubble, using the 100-inch Mount Wilson telescope, was able to resolve individual stars in the Andromeda Nebula, now known to be the nearest spiral galaxy to the Milky Way. The Milky Way, with perhaps 300 billion stars, was seen to be but one of hundreds of billions of other galaxies. More astonishing, perhaps, was Hubble's discovery, achieved by measuring the light spectra of distant nebula, that these galaxies were receding from us at a speed of hundreds or even thousands of miles per second. It appeared that the universe was expanding very much like raisin bread baked in an oven. No matter which raisin or galaxy an observer inhabited, the expansion would look the same. The implications of an expanding universe were staggering. Expansion meant that at one time, all matter could have been compressed together with enormous density. It meant that the confronting idea of a stable, eternally unchanging, and perhaps infinitely old universe had to be replaced by the notion of an evolving universe of finite age. From the point of view of the non-scientist, the theory called into question conventional beliefs about eternity, while also holding out the stunning possibility of a beginning. Over the years, some scientists dissented from the Big Bang theory. In the late 1940s, for instance, Herman Bondi, Thomas Gold, and Fred Hoyle proposed a steady-state cosmology, in which there was no beginning of time. Instead, it postulated that the universe had always existed and would continue expanding forever while always looking approximately the same to any observer. The steady-state model was elegant and, in a way, philosophically pleasing. The abrupt creation of the cosmos in an instant of time was avoided, and life was free to evolve on planets to eternity. Our sun might run out of fuel in some billions of years, but there would forever be new stars to take its place. But a serendipitous discovery by two Bell Laboratory scientists in New Jersey in 1965 sounded like the death knell for the steady-state idea. In reconditioning a large microwave horn antenna, Arno Penzias and Robert Wilson picked up a persistent low-level electronic noise that remained no matter what they did or in which direction the antenna was pointed. They even suspected that the bird droppings in the antenna had something to do with their problem for a while. But they and others soon realized that the omnipresent hiss was the remnant birth cry of the Big Bang explosion echoing through space and time. They had detected uniform microwave radiation whose present frequency, measured by scientists as temperature, indicated that it came from when the universe was much hotter. The temperature and uniformity of the radiation fit perfectly with the model of a Big Bang explosion that occurred 10 to 20 billion years earlier. Steven Weinberg, a Nobel laureate in theoretical physics, described the Big Bang in his book, The First X3 Minutes. With our three-dimensional sense of space, it is not easy for us human beings to grasp the concept of an expanding universe. When we hear about the Big Bang explosion, we are apt to think of highly compressed matter exploding into a larger or infinite space. But this is not correct as applied to the Big Bang. What happened was that all the space, along with the matter and radiation it contained, expanded from a small point. This theory does have certain moorings in everyday common sense. For instance, one can picture without too much difficulty a finite, balloon-like universe in which all the inhabitants are flat creatures living on the surface of the expanding balloon. Their two-dimensional space could expand from a time of very great curvature to a time of a smaller curvature, yet the creatures would find it difficult to imagine their two-dimensional world expanding into something. Albert Einstein envisioned a space traveler circling back to his starting point no matter how he tried to hold a straight line. In other words, we are creatures with a conceptual problem arising from the fact that there are three dimensions of space, and time as a fourth dimension are bendable by nature in ways that we can't easily perceive. When radio astronomers pick up background microwave radiation, they are really measuring the temperature of a very early phase of the universe, reduced by the proportion by which the universe has expanded since its origin. When the universe was 1,000 times smaller, the temperature was 1,000 times hotter, some 3,000 degrees on the Kelvin scale instead of the present 3 degrees. A Kelvin degree is equal to a degree of centigrade temperature, but the Kelvin scale begins at minus 473 degrees centigrade. One of the most noteworthy features of the physical universe today is the predominance of hydrogen and helium, virtual proof of the early high-temperature state of the universe as conceived in the Big Bang theory. Helium makes up about 28% of the massive particles in the universe by weight, and hydrogen makes up the rest. There are only trace amounts of heavier elements produced by explosions of huge stars. The relative abundance of helium and hydrogen can best be explained by the billion Kelvin degree temperatures of the universe when it was only 3 minutes old. This temperature would have cooked up just that helium abundance from hydrogen nuclei present after the Big Bang started. In those earliest moments of the Big Bang, temperatures exceeded 100 billion degrees Kelvin, and the density of matter was billions of times that of iron in earthly conditions. A maelstrom of subatomic particles and radiation swirled. Particles called neutrinos, which may not have any mass, stopped interacting with other particles and became independent ethereal background to the rest of the matter in the universe. Until 700,000 years into the Big Bang, radiation and matter were in equilibrium. But finally, sufficient cooling due to expansion took place, so negatively charged electrons could combine with the light atomic nuclei to form true atoms. The universe lost its opaqueness, and the stage was set for the evolution of all structures we observe today in the universe: galaxies, stars, planets, and even cosmologists who try to figure it all out. But going back to the earliest time before the first hundredth of a second of the Big Bang, there is strong evidence that forces of nature were unified in one all-encompassing force. Without a theory about this force that unified all forces, there can be little understanding of how nature operated when the universe was much smaller and much hotter, and therefore, there can be no adequate explanation for the universe's beginnings. Even though it is impossible for physicists to duplicate in laboratories the high-energy conditions of the early universe, they must develop theories to explain how the forces of nature we observe today came to have 4 distinct characters and how these forces are expressed in an Alice in Wonderland realm of subatomic particles, which includes things called quarks, gluons, muons, tauons, W and Z particles. Physicists are attempting to build the unified field theory edifice once sought by Einstein. Theories of this kind are known as grand unified theories, or less elegantly, GUTs. The GUTs are at the core of understanding what the universe was like at the beginning, and they help predict what we should expect to find in the cosmos today. The 4 basic forces of our present universe were not always seen as having much in common, but there was mystery about them for a lot of speculation on how they might be related. The discovery of W and Z particles reported last year confirmed that electromagnetic and weak forces are truly different manifestations of the same force, an electroweak force. Hence, two of nature's forces have been unified, even if laboratory experimental evidence cannot be developed to show the unification of the strong force in gravity with the electroweak force. The largest experiment of all, the Big Bang, may prove to be the ultimate test of further GUTs, which unify all the forces. This is where cosmology and particle physics may already have joined to provide answers to common puzzles. But until Alan Guth, an intense physicist in his early 30s, walked onto the stage in 1979, there was no cosmological theory to explain how the Big Bang was initiated before this first hundredth of a second. The mind-numbing rapidity of this exponential expansion, which occurred virtually instantaneously and was then over, powered the universe into being. In a minute fraction of a second, the universe expanded from below subatomic dimension by a huge factor, 1 with 50 zeros after it, yet was still only about 4 inches in diameter. From then on, the universe's expansion rate tamed and became uniform with time. In one breathtaking vision, Guth explained several major problems plaguing cosmologists. Guth's theory helped answer why the universe is remarkably homogeneous on a large scale and isotropic. It looks the same to any observer looking in any direction. One would have expected regions of different densities coming from an initially chaotic soup, but according to Guth's theory, the extreme rapidity of the inflation had the effect of smoothing out disparate regions. Moreover, Guth provided a convincing explanation of the greatest enigma facing cosmologists. Why was the universe so precariously balanced between being open and closed? For a long time, cosmologists had known that they had a missing mass problem if the universe was to expand forever, or even if it was poised between being closed and open. All mass in the universe exerts a gravitational force on all other mass. This puts a brake on the universal expansion, and if enough mass is present, the universe might collapse back on itself. But calculations showed that the observable mass in the universe constituted only 1% of that required for it to collapse back onto itself. Some scientists inferred that there was enough heretofore invisible matter in the clusters of galaxies to provide some of the missing mass. Still, this additional mass would perhaps account for only 10 to 20% of the mass required for a collapse. The remaining 80 to 90% of the universe's mass needed for the balancing act may exist in some other form. One explanation was that the missing matter was in the form of black holes created long ago when the universe was highly compressed. It was also thought that perhaps the ghostly neutrinos, which pervade space, have a small mass after all. Even if these particles had only a very small mass, they could account for a deficit and, in fact, might comprise the major fraction of mass in the universe. The inevitable mathematical consequence of Guth's theory is that the universe is perfectly balanced between being open and closed. According to Guth, inflation also implies that the universe is billions of times larger than the currently observable universe, which is itself billions of light years in extent. If the universe had more than the critical density of matter, it would collapse back in on itself many billions of years hence, and all vestiges of structure would disappear. Some have suggested that it would then bounce and re-expand in a new Big Bang. So the present incarnation of the universe might only be one of many of infinity of foregoing universes which might or might not resemble our own. But the new cosmological thinking is that at least our observable universe will expand forever, even as gravitation inexorably slows the stretching of space, but not quite to the point of stopping. In other words, the expansion is destined to go on forever, a concept that bothers human minds that have a great difficulty grappling with the notion of infinity. Now that you've watched the video, what do you think about the universe and its existence? Let us know in the comments section below. Thanks for watching.